Okay, so today we are going to talk about the TI microcontroller board, okay, or TIVA series, and we will use this board in our course. Okay, so first of all, this is the board which we are going to use in our course. Okay, so in this board we have USB connector which will be used to provide the power, as well as it can be used to program the microcontroller. So if you see here, there are two microcontrollers, this one here in the middle and here in the top. Okay, so this section, top section, okay, this section is used for debugging purpose. Debugging purpose means you can run the program, and in the hardware itself you can check how the program is being getting executed step by step. So you can stop the programming or stop the execution of the program according to your wish. So that is why we have this debug section. Okay, so this part will help you to debug the microcontroller or debug the program. Apart from that, we have connectors here. You can see, let me just make any other color, yellow. Okay, in this area you can see some connectors are there. Okay, so you have lots of connectors or lots of GPIO pins which you can use to program the or to connect with the external world. Similarly, here you have the crystal oscillator. Okay, apart from that, you have two switches, switch number 1 and switch number 2 for the user. Okay, so you can directly program the microcontroller board and use these two switches to check some programming. Here you have a similar one more switch which is reset. So if you want to reset the microcontroller or restart the programming from the very first line, then in that case you can press this button, so reset button. Okay, just like Arduino. Apart from that, you have one more button here, sorry, one more connector here. Okay, micro USB, which can be used to connect with the device when we are saying here this microcontroller. Okay, and there is a small LED which can generate three different colors here. Okay, which is RGB. So that means red, green, blue. All the three LEDs are within this particular LED. So you can generate three different colors, or you can even pass a combination of these colors to generate any other color, because you know almost all the colors are generated using RGB. Okay, so let us move ahead. So let me just go to the reference. Okay, because this will help you to understand what are there in the microcontroller board. So this I have shared it with you in the classroom. Okay, this is the user guide for TM4C123G launchpad. So this is the microcontroller board provided by the TI, and it is only of 28 pages. So it has got only small details regarding the functionality and features of the microcontroller board, which we will discuss in this lecture. Okay, apart from that, you can go through the details of the microcontroller, the circuit connection, and which pins are connected to the LED, which pin is connected to the switch. For example, here you can see the pin number, port PF4. Okay, PF4 is connected with switch number 1. PF0, port F0 is connected to switch 2. And then we have PF1 red, RGB LED red, PF2 blue, and PF3 green. So in this way you can go through this particular microcontroller board's manual, and you can see what are the available pins and which pins can be used in which kind of function, which pin can be used for different types of functionalities. Okay, so please do visit that manual and go through it at least once to understand what are there in the microcontroller board. So what are the main components in the MCU or the microcontroller? So we have full speed USB. Okay. Apart from that, we have 632 slash sorry 16 slash 32 bit timer, or we can call it general purpose timer, and in short it is written as GPTM. So 6 general purpose timer, and then again 6 32 slash 64 bit timer. Okay, so there are 12 timers, and 6 are 32 bit, or we can say 16 bit. And if you combine, for example, there are two timers, timer A and timer B. Okay, timer A and timer B. Okay, and these two either can be used as 16 bit. Okay, or if you combine these two, they will make a 32 bit timer. Similarly, you can use two 32 bit timers separately, or combine them to make one 64 bit timer. So there is one timer. So timers are available with you. Then two PWM modules are there, pulse width modulation, which are used to control the speed of the motors or the intensity of the light and so on. We will try to explore them if we get enough time to cover these topics. Apart from that, two watchdog timers are there. Do you know what are watchdog timers? Any idea what are watchdog timer and why they are used?
No, sir.
Okay, for example, suppose you are using a microcontroller board, and you know that your microcontroller or the program in that microcontroller will take, suppose, okay, take 500 millisecond to complete the whole program. Okay, and then after 500 millisecond the program should restart. Okay, so in this way the program is running smoothly. But sometimes what can happen, you can have some unwanted what to say interrupt, or some unwanted what to say programming error or something. Okay, or conditions which we have not checked in that case. So in that case what will happen, the program will take more than 500 millisecond. So at that time we cannot go and keep on resetting the microcontroller again and again. So for that we can use watchdog timer, and watchdog timer keeps an eye on this particular time, and if the program has not returned back within 500 millisecond, watchdog timer will automatically restart the microcontroller board. So for example, where we can use this particular facility, suppose you are sending a spacecraft, okay, in moon or somewhere else which is far from your locality. Not only moon, maybe some other city in case. And now you cannot go and reset the microcontroller board again and again by going to the next city. So what you can do is you can use this particular microcontroller's feature, watchdog timer, which will keep an eye on the time taken by the microcontroller to finish the program. If the program is not finished within that particular specified time, watchdog timer will reset the microcontroller and restart the program again. So you don't have to go and restart or reset the microcontroller again and again. It will manage that thing. Okay. Okay. So there are ports available for serial communication. We can say 8 UART means these are for serial communication. Okay, serial communication. So 8 UARTs are there, 6 I2C protocols based ports are there, and 4 SPI modules are there. Okay, or even we can call it SSI, synchronous serial interface. So there are enough ports for communication. Okay, for example, if you just want serial communication, use UART. If you want I2C, I2C uses two lines, okay, to communicate with external devices, and SPI uses four lines to communicate with external devices. So it is your choice. You can use either UART, I2C, or SPI depending on your choice. But you should know what kind of features are available in this particular communication modules. We will cover this part definitely. Okay. Next, then we have two quadrature encoder interface QEI. These are generally used for maintaining the speed of the motor or checking the RPM of the motor or even the phase of the motor which is running at a particular speed. So these are very important nowadays in automobile sector. Okay, so if you are interested in controlling the motor speed, the phase of the motor or the RPM of the motor and all, you can use this particular quadrature encoder interface. This is very good feature which is provided by the microcontroller. And apart from that, you can push this microcontroller to low power consumption mode, or you can say deep sleep mode or sleep mode. Okay, in that case you can reduce the power consumption by the microcontroller. So intelligent low power design, we can say hibernation or hibernating mode are available. Okay, so these are the overall features of the microcontroller. Okay, let us go through the block diagram, because block diagram helps us to understand how the microcontroller is going to work. So just keep an eye on the block diagram because this is very important. Okay. Okay, so first of all, here you have, I hope you can see this. Hello.
Yes,
Hello.
sir.
Okay, so here you have the microcontroller. Okay, ARM Cortex M4. Okay, and it can run at a speed of 80 megahertz. Can you tell me what is the speed at which Arduino Uno works, or the clock speed for Arduino Uno you might have used in the design lab? What is the speed which is provided by the Arduino Uno? Because this is very important, because when you choose a microcontroller, these kind of features you should know, that whether the microcontroller can work at 80 megahertz, 16 megahertz, 20 megahertz. What is the speed? For example, 8085, it can go, or it can work in 3 megahertz to 5 megahertz. Okay, here you have 80 megahertz microcontroller. Okay, so it is very fast. Apart from that, like I said before, floating point unit is there within the microcontroller. Okay, memory protection unit is there. Memory protection unit is needed because sometimes your program may jump from one memory location to another memory location which is restricted. For example, stack can overflow and go into the code memory location which is not allowed. Similarly, code, sometimes if you are writing a very big program, the code may enter into the RAM or something which is not allowed. So those kind of memory protection unit is there, so that memories are not overwritten or corrupted by any program. Apart from that, we have nested vector interrupt controller, which will handle all the vector interrupts which are available in the microcontroller. There are so many vector interrupts which are available in this microcontroller, somewhere around 240 or so. Okay, then we have JTAG. Okay, this is used to communicate with the microcontroller. So when you are programming the microcontroller, you are using JTAG. Okay, you have the ROM, flash. Okay, flash containing somewhere around 256 KB. Okay, and then you have system bus. Here you can see system bus. And now let us look into one of the most important feature of this particular microcontroller. There is a bus matrix. Bus matrix means there is a bus matrix unit which actually manages different types of buses. Okay, what are the different types of buses available? Okay, so let us check here. So important is system control and clocks. So this system needs very high speed per bus. Similarly, you have DMA, direct memory access, EEPROM, GPIOs, watchdog timer, hibernation module, general purpose timer. So basically, there are two important buses in this particular microcontroller. One is called Advanced High Performance Bus, AHB, and the other one is Advanced Peripheral Bus. So this is legacy bus. Legacy, when we say, it means it was available from the past also. So ARM, what it did, it kept the previous micro bus structure. At the same time, it introduced one more advanced high speed performance bus. Okay, what is the difference between these two? Advanced high performance bus can be used to execute your program in a very fast manner. Okay, it will take only one cycle to complete task in AHB, but in APB it generally takes minimum 2 cycles. So if you keep an eye here, all the peripherals are not connected to AHB. For example, watchdog timer. Watchdog timer is only connected to APB. You see here, watchdog timer is connected to APB. Similarly, hibernation module, again APB. General purpose timer, APB. But if you take an eye or keep an eye on this particular GPIOs, GPIO means the ports. In that case, you can see ports are connected to both AHB and APB. So it is on you whether you want to use the GPIO pins using AHB or APB. Okay, EEPROM. EEPROM, because EEPROM is very fast and we need to keep it very fast. So therefore, you can see it is connected to AHB. Okay, USB OTG, AHB. Okay, now here, for example, SSI. Okay, this is serial communication protocol module. So communication module, they don't support mega hertz of speed and so therefore they are using APB. Similarly, UART APB, I2C APB, CAN APB. So all the serial peripheral modules mostly are connected to APB except USB. USB needs faster communication protocol. So therefore only USB is connected to AHB. Rest of all the communication modules are connected to APB. Now coming down, analog comparator is there, which is connected to APB. 12-bit ADC channel, analog to digital converter, connected to APB. Similarly, PWM module connected to APB, and quadrature encoder interface is connected to APB. So this is very important to understand that there are two buses. One bus supports very high speed data rate. The other one provides a bit slower data rate, and both buses are there, and we can use any of these two buses depending on our choice. Okay, so in future when we will be using programming, we can use any of these two buses for our GPIOs or DMAs or any other peripheral. Okay, any doubt in this part? Any doubt? Because this block diagram, if you can understand or if you can remember the block diagram, then it will be very helpful when you will be writing a program. Otherwise, you will be getting confused why we are using AHB, why we are using APB, and sometimes you may write a wrong program, for example, UART, and you might try to access AHB. That is not allowed. So you will get bus handling error. Okay. So this kind of errors may generate if you are not using proper buses for your programming. Similarly, there is functional block diagram. Functional block diagram is almost the same. Okay, here you can see functional block diagram actually talks about all the peripherals and how the peripherals are connected. So ICDI, that means the communication with the external world. You can use this line to program the microcontroller. Okay, JTAG. And then you have UART, USB. So rather than functional block diagram, if you can keep an eye or if you can remember the main block diagram, that will be more helpful. So there are two basic diagrams. One is block diagram and other one is functional block diagram. Okay, I have discussed about there are two buses, APB and AHB. Okay, so in short, this is the different packages or different peripherals which are available with the microcontroller. Okay, the microcontroller itself 80 megahertz, which contains JTAG and NVIC, okay, MPU, FPU in ETM, and similarly you have memory, flash memory, SRAM, ROM, EEPROM, and then you have analog section where you can have voltage regulator, comparators. Three comparators are there, analog to digital converters, 24 channels, so you can use 24 pins for analog to digital converter. So too many sensors you can connect. Then inbuilt, there is a temperature sensor also in this board. So there is an inbuilt temperature sensor which you can program. Then you have serial communication module, so where you have 8 UARTs, 4 SPI modules, USB module, CAN, CAN architecture is generally used. I have discussed about this in the past also. These are used in automobiles nowadays. So if you are interested, you can have CAN network and you can learn it, which will help you to get easy jobs in automobile sector. 6 I2C modules are there. Okay, so there are serial modules. Then you have motion control modules. Motion control, like I said, motors and all. So two QEIs, then 16 PWM outputs, timer are there, comparators, PWM generator, PWM interrupt is there, and all. And system related blocks are there, like clock, system control, SysTick timer, and then you have 12 timer, PWM, and compare, and I'm forgetting this CCP. Compare this anyway. This is there. Anyway, leave it. Two watchdog timers are there, GPIOs are there, general purpose input output, DMAs are there. So 32 pins you can use for DMA, direct memory access. Inbuilt precision oscillator is there, and battery backed hibernation or hibernate module is there, which you can use for sleep mode and deep sleep mode. So this is all about the block diagram. Okay. So if you take the microcontroller board, these are the pins available with the microcontroller board. Okay, but unfortunately it is not very uh, it is not that much helpful, because in Arduino you have separate sections, and those sections contain only that kind of pins, but here all the pins are almost, what to say, mixed up. So you have to check this particular diagram to know which pin is going to work in which particular fashion. One more thing, like in case of Arduino, each pin can work in multiple ways. For example, PD, here you can see digital read or digital write port. So all the pins, okay, are digital read or write enabled. So you can use it as a digital input or output. Apart from that, some pins are analog read, okay, which are dark blue in color. So A7, A6, A5, A0. So these are analog read. Similarly, A9, 8, 9, 10, and 11. So these are analog read pins. And apart from that, if you need SCL SDA for I2C, communication can take place. And then these pins, CS, SCK, MISO, MOSI, these are used for SPI communication. So depends. Okay. So one pin can function in 2 or 3 different ways, like digital input output, analog read, communication I2C, or here SPI communication. So that means before you want to use this particular pin for your any project, you must first tell the microcontroller that I am going to use this pin, okay, for analog reading or digital reading or digital read write or SPI or I2C communication. So before using the pin, you must define the functionality, because there are multiple functions available with the pins. Okay. So what are the features? I have discussed about it. You have ARM Cortex M4, 80 megahertz microcontroller. Okay, have you heard of 100 this DMPS? DMPS? Hello?
No, sir.
No. For example, this is one important term. Okay, DMPS. I think Dimitri million some. Okay, instructions per second, something like that. Let me check, because this feature DMPS. Okay, so what is that? DPM? DMPS? Yeah, DMPS. I'm just forgetting the full form. No, it is not DMPS in that case. DPMS? No, full form. No, let me just check. Million instruction per second, something like that. Okay, no, I'm not getting it. I will find it. Okay, don't worry. Okay. Okay, what is the use of this particular parameter, first of all? So suppose you have a microcontroller which works at 50 megahertz, assume. Okay. And there is another microcontroller which works at 70 megahertz clock speed. Okay. So sometimes due to the benefit of the architecture, even microcontrollers which are working with slower clock rate can perform faster execution of the program. For example, like I said, ARM Cortex M4 can support 16-bit and 32-bit both instructions. So it is actually optimized for both. Okay, so that means, okay, so now here in this case what happens, now it is very difficult to tell which microcontroller is fast. So what happens, we use this particular terminology. Okay, so there is one program which is written, okay, which contains suppose somewhere around 1000 or 2000 lines, assume, and both these microcontrollers are loaded with that program and executed, and then they are compared which one executes the program fast. Okay, so this is actually used to check the speed or relative speed of different microcontrollers. I'm forgetting this, not feeling well anyway. So now coming to flash. Okay, so we have flash memory 256 kb, SRAM 32 kb, EEPROM 2 kb, and internal ROM. Okay, communication interface, I told you UART, SSI, I2C, CAN, and USB. Okay, analog support, we have discussed this one also. Okay, and system integration, we have discussed about this one also. Anyway, now these we have discussed previously. Yeah, CCP, capture, compare, PWM, capture and compare, PWM. So for most important part is this one for us, because we are going to use this microcontroller to program the GPIO pins. So there are 43 GPIO pins which can be used for our input and output functionalities. In case of Arduino, we had 14, somewhere around 14 GPIOs available in that. So you have lots of GPIO here. So you can connect lots of devices with this microcontroller. Okay, now okay, I have discussed about all this part. Yeah, this is important. Programmable control for GPIO pad configuration. There are two options available: weak pull up and or weak pull up or pull down register. Weak pull up and pull down register I have discussed previously also. You know, pull up and pull down registers. Whenever we use switches, we use pull up and pull down configuration. Weak pull up, when we say, okay, in that case, the resistor which is used for pulling up or pulling down, okay, is a very high impedance resistance. For example, like this. Okay, so you have the switch here and ground, VCC. Alternative circuit is this one, where you have the switch and then you have the resistance. Okay, R switch and switch. Here you are taking the output. Here you are taking the output. Now this is called pull up. Okay, pull up means you are putting this pin by default to high voltage. This is called pull down because you are by default connecting it to ground. When we say weak pull up or weak pull up or pull down, okay, pull down. In that case, this resistance, okay, which we are using will be of high impedance. High impedance. In general, they are somewhere around 50 kilo ohm. Okay, depends, but in general 50 kilo ohm. So there are weak pull up and weak pull down resistors inbuilt in the microcontroller, so you don't have to connect external resistances for your circuits. If you need, you can, but in general you don't need because they are inside the microcontroller itself. Okay, you can use or you can drive these pins or the GPIO pins at different currents. For example, 2 milliampere, 4 milliampere and 8 milliampere. For that, you can configure some registers inside the microcontroller and you can force the GPIO to generate 2 milliampere current, 4 milliampere current or 8 milliampere current. That is the programmer's choice. Okay, and it can sync. That means the microcontroller or the GPIO pin can sync 18 milliampere. When we say syncing, that means the current is coming towards the microcontroller pin. For example, like this. For example, like this. You have the switch here. Okay, this is connected. So resistance is there, VCC is there. So when the switch is off, then definitely this current is going towards the microcontroller because this is going to connect with the GPIO pin of the microcontroller, right? GPIO pin of the microcontroller. So the current, when the switch is off, the current is going towards the GPIO. Okay, so this is called syncing of current. Sync, okay, or current sync. Okay, syncing current. Okay, because the current is going towards the microcontroller. So at max you can go for 18 milliampere sync current. If you go more than that, definitely you will be going to damage the GPIO port. So be very careful when you are using this particular resistance, because VCC, if suppose you are using 5 volt, then in that case you must be very careful with this resistance. You should not use 10 ohm or 100 ohm because that may generate high current towards the GPIO and you might damage the GPIO port. Okay, clear? Next, these are very important features, but we cannot cover all the things. Okay, you have open drain enable features and all. Anyway, configuration procedure. So first of all, suppose you want to
Sir, your screen is not visible.
not visible. Okay, wait. Actually, today I'm having high fever, very high fever. But let me just high fever is there, headache is there. Anyway, now it is visible.
Yes, sir.
Okay. So let us talk about how to configure or how to use GPIO pins. Okay. So, for example, like I said, we have LEDs and switches which are connected to port F pins of the microcontroller. So to enable the GPIO, first thing that we need to do is to enable the system clock of that particular GPIO. For example, when we say GPIO, you have A, B, C, sorry, D, E, F. So if you want to enable or to use any particular port, suppose you want to use this port, port F, pins of port F. In that case, first thing that you need to do is to enable the clock to this particular port, because by default all the ports are not connected to the clock, therefore they are deactivated. Okay, so the moment you connect the clock, the port gets enabled. Why the clock is not connected directly to the port by default? Because the microcontroller want to save power. Okay, so to save power we need to keep the clock disconnected. Okay, and once the clock is connected, okay, then only the port will start working. So the first thing that we need to do is to connect the clock. Okay, so that is called clocking, or we can call it system clock, or we can call it clock gating. Okay, this is the technical term, clock gating. So first you have to connect the clock or enable the clock to particular GPIO. Then after that we have to configure the operational mode of the that particular pin. Mode, when we say mode, we have to tell whether it is input mode, output mode, parallel, serial, or some special function like ADC, okay, DAC, or you can use it for UART, okay, or any other particular task. So first you have to provide the clock, then you have to tell the operating mode, then after that you have to check whether any interrupt has to be enabled or disabled. Okay, then after that you can use some peripheral driver library which we'll be using after 2 or 3 lectures, okay, to control the pins of the GPIO. Remember, every GPIO can perform multiple functions such as ADC, DAC, timer, and all. For that, you can go to this manual, okay, and see here. For example, table 10.2, and you can see here port A0, port A1, 2, 3, 4, 5, 6, 7. Okay, so port A0 to A7. Now, in the microcontroller, these port PA0, 1, 2, 3, 4, 5, 6, 7 are represented by pin number 17, 18, 19, 20, 21, 22, 23, and 24. Apart from that, PA0 can be used for digital input output. Of course, every pin can be used for digital input output, but alternate function you can see here. You can use it for UART receiver or UART transmitter. So PA0 can be receiver, or it can also work. PA1 can work as a transmitter. Similarly, if you come right, okay, here, it PA0 can be used for CAN 1 receiver, and PA1 can be used for CAN 1 transmitter. So alternate functions, or we can say each pin can have more than one function. Okay. Similarly, PA2, 3, 4, 5 can be used for SPI communication, clock, SS, MISOMOSI. Okay. Similarly, there are multiple features which are available with different pins. So before using any pin, you must know which kind of functionality you want to enable in that particular pin. Okay. Now coming down, please refer to this table and keep it with you when you are writing a code. When you come down, you can see here, by default, whenever you restart a microcontroller, okay, whenever you restart a microcontroller or this microcontroller, by default, the pin will be in the shaded gray mode. Shaded gray mode means, for example, when you restart the microcontroller, PB2 and 3 will be by default in I2C SCL and I2C SDA by default. So if you want to change it to CCP0 and CCP1, then you will have to change it. Otherwise, by default, they will be I2C clock and data. Similarly, PC0, 1, 2, 3 can be for timers, different functionalities. So the gray areas are, or gray, okay, are those functionalities which are by default enabled when you restart a microcontroller. Clear? So now there are so many things to remember, and don't have to remember. Preferably use the data sheet and user manual to explore more about the features. Okay, this I have discussed with you. Okay, ARM Cortex bus interface, leave it. Memory architecture. Okay, so there are basically 5 buses available with your microcontroller. One is I-code bus, decode bus, system bus, PPB, private peripheral bus, and AHB, advanced high performance bus. So whenever you are using code, opcode, okay, from the flash ROM, that opcode goes through this, or it is using this particular line, I-code bus. Okay. When you are reading data from the flash ROM, you are using, or the microcontroller will be using decode bus. Anyway, you don't have to go in this depth, okay, to understand the functionalities, because when you are writing a program, these things may not be that essential, but to know that bus matrix is not a simple bus in the microcontroller. It is very complex bus matrix available in the ARM. So opcodes are carried by I-code bus, data are carried by decode bus. Okay, read, write, and internal peripheral devices like NVIC and all are generally used by, or they are handled by system bus. And similarly, the high speed GPIO or any read write operation are done by AHP. Okay, so these are the 5 different buses. Now let us talk about programming the microcontroller. So we have discussed about preprocessors and macros in C, and now we are going to correlate why we covered preprocessors and macros and how they are going to be helpful when we are using embedded C program. Okay, because whatever we have covered in C programming, they are very important and they are generally used in embedded C. Okay, the preprocessor makes the code readable and convenient. For example, I I believe you know this particular code. What is this code doing here? This bracket. Unsigned int star within a bracket. This thing, this is what in C programming. We have discussed this part.
It's a pointer.
Okay, wait a second. First of all, this thing, have you gone through such data? What is this particular thing doing here? It is a hexadecimal data. Clear? It is a hexadecimal data. And of course, this is nothing but an unsigned, because U is representing, it is unsigned, right? Unsigned hexadecimal data. Now, this bracket, first bracket, unsigned int star. What is this bracket doing? You are saying this is pointer. If it is pointer, then what is this thing doing? Pointer starts with star, right? If you are going to declare a pointer, you generally declare it like this, right? And when you are using this kind of bracket, what it is doing? I told you, dereferencing, sorry, dereferencing a pointer, okay? Dereferencing. We have discussed about how to declare a pointer. For example, if you declare it like this, int asterisk p, right? And then what we do? For example, int a, int a. So this is a variable a, and then we declared a pointer. Then next step, what we do? We declared a variable, declared a pointer, and then third step. Anyone? What is the third step in general when we write program in for pointers? How to attach the pointer to a variable's address? What is the code that we use to attach the pointer to the address of a variable? Because we have declared variable, declared pointer. How to attach the pointer to variable? Anyone? अरे भाई, if you can recall, ampersand sign, what it does? Am I
The
connected?
address to variable A.
So now the pointer is attached to the address of A, and then now either you can change the value of A, such something like this, A equal to 5. You can use this approach to enter a value to the A, okay, or variable A. Alternate way is using pointer. How we do? How we do the changing the data inside a variable using pointer? That is called dereferencing. Asterisk p equal to 5. These two are same. Is it correct or not? Hello.
Yes, sir.
So now here you can see what we are doing here. First thing we are, okay, this pointer, okay, is dereferencing this address, and in that address we can enter a value directly. What is the value? 20u. Again, it is hexadecimal unsigned number. And this bracket is not, sorry, dereferencing is this whole sorry. This is not dereferencing. Dereferencing is the whole bracket from here to here. This is dereferencing. And this is what is this thing doing? This bracket doing here. Dereferencing is asterisk, then the address, and you can enter some data into that. But what is this block doing here? Typecasting. So what we are doing here, we are taking an address, typecasting that address, and dereferencing that address to enter a value. So in this way, we can go to any particular address and then we can enter a value to that particular register. So this particular register, okay, can be a GPIO or something. So this is first approach to enter a data into the register by using typecasting and your dereferencing. Apart from that, now we can use preprocessor like define, because you cannot keep on writing this program throughout the this kind of code throughout in your program, because this is very complex. So what we can do, we can define it like this: RCGC GPIO. Okay, you can name it anything. Okay, it's your choice. Okay, you can call it sys underscore clock. Okay, because you know preprocessor can provide any name. So define, and you define this whole term, okay, with a simple name which is more meaningful. So then after that, what you can do, you can use RCGC GPIO and enter the data. So the whole this particular command, okay, this particular command can be defined with a simple name, and you can use that simple name to enter the data. Is it clear?
Yes, sir.
So this is how macros or preprocessors are used to simplify our life. So let us go through some codes and try to understand that. Okay. Okay. So I would recommend you to first open the data sheet. Okay. Open the data sheet. Okay. Open the data sheet, and then not this one. Reference manual. Okay. In this first thing, like I said, to enable any GPIO, first we need to connect the clock to the microcontroller GPIO port. Okay, so for that you can go to here, RCGC GPIO. Okay, search general purpose input output run mode clock gating. Let us go next here. Okay, let us go next. Okay, this one is your GPIO clocks enabling register. So first we have to enable the clock. Okay, so you can read this register 60 general purpose input output run mode clock gating control register. Okay, so for example, what is the base address here? You can see the base address. Base address is 400F E000. Okay, and the offset is 608. So what is the total address of this particular GPIO register or the clock gating register? It is 400F E608. Okay, so now let us see what is there inside this particular register. Inside this register, like we know that ARM Cortex M4 uses 32-bit registers. So 0 to 31. So these are the bits of those that particular register. And let us go a bit down and see here. 31 to 6 is reserved, so we cannot use it, or we shall not use it. 31 pin number 30 or bit number 31 to bit number 6 are reserved, so we shall not use it. So there are 0, 1, 2, 3, 4, 5, 6 bits which are available for read and write purpose. Let's go down and check. Bit number 5, this one, R5, okay, bit number 5 is used to enable the port F mode clock gating control. So to enable the clock of port F, we have to use bit number 5 or R5. So if you make it 0, port F is disabled. If you make it 1, port F can be used in the run mode. Similarly, for port E, bit number 4, come down, bit number 3 for port D, bit number 2 for port C, and port A and B are 0 and 1 respectively. Any doubt in this part first? Why we are using this register? This register is to provide the clock. For example, if you read here, RCGC GPIO register provides software capability to enable and disable GPIO modes in run mode. When enable, the module is provided a clock and accesses the module registers are allowed. So until unless you provide the clock, port F or port A or port B, any ports, okay, pins you cannot use. When disabled, okay, the clock is disabled to save power and access the module registers, generate bus fault. So if you have disabled this particular RCGC GPIO or clock, and then if you try to access port F or port A as any particular pin, then it will generate a bus fault. Okay, it will generate a bus fault because the clock is disabled, so you cannot access that pin. Okay, any doubt in this part? First, how to decode the address? You go down, every register will have its own base register address. Okay, here you can see base register address and then an offset address. You add these two, that will make the final address of that particular register. So GPIO, RCGC GPIO register's address is 400FE608. And to enable port F, okay, we need pin number 5. Why we are enabling port F? Because switches and LEDs are connected to port F for our initial programming. Okay, now come down. This is done. So if you check here the program, okay, the program. So here you see define, hash define, okay, RCGC GPIO, and then the address of that particular register. Why we are using this particular term? Asterisk, bracket, unsigned int, asterisk, and then the address, so that we can directly enter some data into that particular address by using. There are two concepts running in the background. One is typecasting and the second one is your dereferencing. Okay. Similarly, you have next line, which is GPIO DIR. Okay. So one way is to go from here directly to GPIO. Okay, general purpose input output. Click on that. Go down, register map. Okay. Here you can see register map, and then you come scroll down. GPIO port A base address is 4000, but provided you are using APB bus. Like I told you, there are two buses. One is legacy bus, which is old version, and the new version. So this is legacy bus. Then if you want AHB, high performance bus, you will have to use 4005, 8000. It is your choice whether you want to use GPIO A in APB or AHB. For time being, we are actually interested in port F. So here we are going to use this particular address. So APB 4000 to 5000. This is the base address. Okay. Then we have to tell the microcontroller that this port's particular pins are going to work as an input or output. So let's go down and check some details. Here, the offsets. So whether you use port A, port B, port C, any port, okay, come down, you will have to use these offsets to go to that particular register. For example, 400 you are using for GPIO, DIR or direction register. So port F's base address, let me just take a notepad and just make a note of this. Okay. For example, port F base address is I'm using APB. Okay. So not AHB, APB I'm using. So it is 0x402 5000. This is the base address. Okay. Now, so this is the base address. Then after that, there are so many registers in each port. These are the registers in each port, available in each port. So port F, go down, and suppose we have to go for GPIO DIR register. Okay, then the offset is 0x400. So if suppose someone asks you what is the complete address of complete address of GPIO DIR for port F, okay, then the complete address is 0x4000 4002 5000 plus 0x400. So that will become 0x4002 5400. Okay, so this is the address for GPIO DIR register. Similarly, if you need to use GPIO data register, okay, then in that case, base address of port F is, we know that this is the base address of port F, right? And then offset. So GPIO data is, the offset is 0x00000000. Okay, so the complete address for port F GPIO data is your okay, same 0x40025000. Clear? Any doubt in this part? Because this is sometimes very doubtful, and of course you should have doubt in this part, what we are doing, why we are going to that register and all. Okay, let me give you a simple example so that you can correlate it. Okay, so you might have used Arduino, right? In Arduino, let me just open it. Oh, come on. Why it is taking too much time? Any doubt till this part? How to decode the port's address, base address, and then the offset of the particular register. Remember, each port, be it port A, B, C, D, any port will have all these registers inside it. Okay, they will provide different functionalities to the pins of ports A to F. And my Arduino is taking too much time. Let me close this. Some of the windows, it is taking too much time. Okay, so if you can recall, I can just go to the basic program, example, basics, and blink. So this was the program in Arduino. I believe you might have used this particular program, right? Anyone? You might have used this program, right? Hello?
Yes, sir.
What is this thing doing here? This code. Pin mode, LED built-in output. What is this particular line doing? Respond, yeah. I am having high fever and still teaching you guys. And you guys are no, I don't know what to say about you guys. I'm going to end the lecture. Thank you.